Yes, thank you. So my name is Osman Unsal, and I will introduce the LEGaTO project in general. And then this is the schedule. Then we will continue with the various presentations on the hardware, heterogeneous hardware stack that will be presented by Jens Hagemeyer. Then we will look at the software stack runtimes. Mustafa Abdul Jabbar will present. We will then examine the programming models. This will be given by Pascal Felber. And then finally, we will look at the use cases at the top of the compute stack. This presentation will be given by Micha von den Berge. And finally, we will have a brief presentation on the integration that we have given by Xavier Martorell. After that, we will have a roundtable if time permits and if there are questions of 15 minutes. So we have some slack. Thank you again. And I think where the project comes from is from the challenge that we have that as we know, Dennard scaling is dead and Moore's law is slowing down. We are trending towards these heterogeneous architectures as a result. And we have an increasing focus on energy. So the ICT sector is responsible for 5% of global energy consumption, and this is expected to rise. So the combination of the need to do something about, let's say, not wasting energy and heterogeneous architectures, the need to program them is a challenge that is taken by the LEGaTO project. So again, reiterating, I think for the future, we shouldn't be talking about flops anymore, but about megawatts, 20, 30, 40 megawatts for supercomputing centers. For exascale computing, the target has been 20 megawatts for some time, but looks like we are not going to hit that. So energy is an important challenge, not only for the supercomputers, but also at all levels in the computing stack. So we were used to exponential growth in computing. However, this is coming to an end due to the Moore's law coming to an end, but also because of heat density issues that necessitated us to go to the multi-core, while we were trying to constrain the power consumption. So this created a challenge, and another challenge was data movement. So the cost of moving data from one, let's say, one compute block to another was the leading cause of power and energy consumption in computing chips. So it's both within chip and also locally between chips. We have to constrain data movement, do local computation, use, for example, the data of the way data flows in the best way as possible. So that brings us to maybe a data flow based mode of computation as an intrinsically energy efficient way of computing. And as part of the heterogeneity, we are now past CPUs and GPUs, and we are arriving at the FPGAs. And one advantage of FPGAs is to be able to, that they are able to build ultra deep, highly efficient pipelines. But how about the programmability of these accelerators, right? So it's still a challenge. So all of these, let's say, different aspects of the issues that we are having today is the topic of the LEGaTO project. So the overall ambition is to create a software stack support for energy efficient heterogeneous computing using a made in Europe software stack. And then running the stack on a heterogeneous hardware substrate composed of CPUs, GPUs, FPGAs, and abstracted data flow engines with the main goal of energy efficiency. The objectives of the project is 1 order of magnitude improvement in energy efficiency, but not energy efficiency in and of a goal by itself, but also accompanied by an increase in reliability, security, and as well as programmability. When we look at how the project is structured, at the heart is a task-based data flow programming model, data flow a model because this enables kind of this naturally energy efficient computing. And this is surrounded by also concern for fault tolerance, security, productivity, all as also design goals at the same time as with energy efficiency, running on heterogeneous hardware platforms. And as use cases, we have machine learning, healthcare, and smart home city use case. When we look at our compute stack, so starting from the use cases, we have smart home, smart city use cases, machine learning and healthcare, as well as a secure IoT gateway, which is a special use case that we have at the edge. All of these use cases come together with the task-based data flow programming model that we call OMPS. And that programming model then feeds in the other components, all of them data flow based, of the other high level compilation and runtime blocks that we have. Shita is an experimental also programming model environment that's task-based and also complementing OMPS more on the research side. We have MaxJ compiler that compiles from the Maxeller data flow engines. But 8 is basically this compiles OMPS code into FPGA fabrics, and defined HLS is a new hardware description language that makes it easier to develop FPGA applications, therefore addressing the programmability challenge. All of these blocks then are transformed into the various runtimes. Nanos is the runtime for OMPS. We have a special product, SCONE, that makes programming with SGX, Intel SGX hardware security extensions much easier and much more efficient, with fault tolerance and energy also built in as well. We have a fault tolerance interface that works across CPUs, GPUs, and FPGAs for unified fault tolerance. And we have the heat scheduler that is energy conscious. That is all mapped into an efficient small form factor HPC hardware units composed of CPU, GPU, and FPGAs. So these are the various partners Chrisman and Bielefeld are working on the hardware side. Machine intelligence is working with the neural network use case. Technion developed a defiant HLS language. Neuchâtel is working on scheduling. Barcelona is working with OMPS. Helmholtz Center is providing the healthcare use case. Chalmers are also working on scheduling. Maxalar has their data flow engines, and Dresden is working on security. So we have, as use cases, we have infection biomarkers. This is statistical application. More details will be upcoming in the work pack in the use case presentation. We have an assisted living smart home use case that includes a smart kitchen, smart living room, smart door, and a smart mirror. So we will be highlighting the smart mirror in today's presentations and how we made it much more energy efficient. We have a smart city use case. It's operational urban pollutant dispersion modeling. So this is, in a way, a pollutant weather prediction on a street-by-street basis. That used to run on the supercomputer, and now we can run it on much smaller form factor devices. We have, in the machine learning, we have automated driving use case, and we have the secure IoT gateway use case as well. So in a snapshot, with the smart city use case, we were able to get a significant energy efficiency using FPGAs. With the healthcare use case, we had phenomenal speed up using DFEs from Maxalar. Therefore, this kind of revolutionized the way our folks were conducting their statistical analyses. The machine learning use case, we have up to 16x gain in energy efficiency using the embedded optimizer from our partner MIS. So a detail of today's contributions in the technical talks that you will see are we will introduce the various task-based data flow runtimes that I mentioned: OMS, Chital, MaxJ, and Defiant. We'll talk about fault-tolerant interface and especially how we applied it for GPU checkpointing in today's talk. You'll hear about heat scheduler. You'll hear about how we are able to obtain a significant energy savings with undervolting and how to balance that with reliability. You'll hear about SCOAN, which is aiming to realize the full potential of Intel SGX. You'll hear about secure task-based programming, hardware malleability through node composition, and you'll also hear about the smart mirror that I just mentioned a little bit ago. And we, last but not least, we have been involved in the energy efficient small form factor standard from HPC. So without further ado, I would like to have my colleagues take it from here. Thank you very much.
Yeah, thanks a lot, Osman, and welcome everyone to the hardware presentation of LEGaTO. I hope you can all hear and see me. Can you quickly confirm?
Yes.
Okay, thanks a lot. So this is the session about the, let's say, lowest level, the LEGaTO hardware. I would like to start off with a quick video introduction of the LEGaTO hardware. Give me a second to bring that up. Okay, I hope you can see this.
The objective of the LEGaTO project is to develop a software toolchain for heterogeneous hardware with energy efficiency as the main focus. The LEGaTO project components are shown here hierarchically, starting at the high level from use cases, the programming model, compiler, and high-level synthesis languages, runtime, middleware, and hardware. In this video, we will focus on the heterogeneous LEGaTO hardware, which supports arbitrary combinations of CPU, GPU, and FPGA microservers, representing all major compute architectures. In order to optimize the different use case applications in LEGaTO, different domains from IoT to HPC need to be covered. Using a microserver-based approach, we can configure the optimal hardware among the cloud, edge, or embedded domain, depending on the targeted use case. While the different microservers are shared between all computing domains, different chassis for integration are available, providing extensive communication and management capabilities. The biggest server chassis is the Rexbox DNEB. Due to its size, it is optimized for scale-out installations, for example in cloud data centers. Rexbox DNEB supports up to 144 microservers in a 3RU enclosure. The Rexbox DNEB comprises different carriers, the high-performance, expansion, and low-power carriers. The high-performance carrier can host the latest x86, ARM or FPGA microservers, and if the expansion carrier is attached, PCI Express cards or hard drives can be added. The low-power carrier can host NVIDIA Jetson TX2 microservers. The mid-range system Rexbox Durin has a similar architecture, but is a scaled-down version, which is perfect for smaller installations and testbeds used for benchmarking of heterogeneous applications. Rexbox Durin supports up to 48 microservers in a 2RU enclosure. The LEGaTO Edge server was completely designed and built in the LEGaTO project. It uses a modular microserver architecture like the Rexbox servers, but focuses on edge and embedded applications. T-Rex supports up to 3 microservers in a 1RU enclosure. Up to 3 different microservers and 2 PCI Express extension cards can be populated. By using these slots, our hardware is able to combine classical computing technologies like x86 or ARM servers with accelerators like GPU or FPGAs in a dynamic way. The Edge server integrates a 40 GB Ethernet backbone as well as a high-speed, low-latency communication infrastructure based on host-to-host PCI Express between the different compute nodes and peripherals. This infrastructure provides various topologies and even shared peripherals across multiple hosts. In contrast to traditional PCI Express switching, not just communication to peripherals, but also direct host-to-host communication is supported. For more information, visit our website and follow us on LinkedIn and SlideShare.
Okay, that's so much for the introduction. I see that there's a question right away, or should I continue with the presentation and have questions afterwards? Okay, I will then just continue. So yeah, having the video as the introduction, you already saw that this is about the LEGaTO hardware. So the basic challenge of heterogeneous hardware, which we are focusing on or dealing with in LEGaTO is on the one hand, as Osman said, that this is probably the domain which we need to focus on for both performance and cost reasons. And nevertheless, there's the developer's challenge of selecting the optimal architecture and in the end programming all this. So this is where LEGaTO tries to help with, and on the hardware side we have this LEGaTO cloud to edge microserver platform that we see here. This is basically a platform that covers or tries to cover most of the domains from cloud computing, edge computing, and also embedded. We are doing this by using a modular microserver architecture. And as you can see here, we are having let's say a quite scalable system, which is the Rexbox DNEB that was also shown in the video before. Then the Durian and the T-Rex, which are all based on microserver modules, which can then also be integrated really in embedded devices if you don't want to use them in a, let's say, cloud or edge data center environment. So then, we will have a look at the architecture of these, first the cloud system, the REXBox. As said, it's a heterogeneous microserver approach, which integrates CPU, GPU, and FPGA technology. So all the major compute topology architectures, and can also integrate specialized accelerators, for example, deep learning ASICs or something like that. It integrates a high-speed, low-latency communication infrastructure, which I will focus later, and is basically a blade-style design. So you have these different carriers, the low power as well as the high performance, which are then slide into these rack. So we are combining these high performance and these low power carriers to then basically have like a big little approach of these different microserver technologies. As you can see here, for the high performance ones, we have the normal x86 ones, so you can have latest Xeon technology, Intel Xeon technology, or AMD Ryzen technology in that system. We are covering ARM v8. You can have a 32 or 64 core 64-bit ARM processor in there, or a quite big FPGA. And we are doing the same for the low power section here. So there we have also the FPGA, the ARM, or the GPU technologies, which can be integrated then at a much higher granularity. So as you see, the same space that we are using for 3 microservers at the high performance segment can be used by 60 microservers for the low power variant. And then this is basically interconnected by different networks. On the one hand, we have the normal compute network, which is basically up to 40 gigabit Ethernet. As an integrated backbone in this system. We have a dedicated management topology that allows you to basically have KVM access to every microserver if you need to. And we have a specialized high-speed, low-latency communication infrastructure in this system that acts as a quite, I would say, high-performance communication infrastructure across those different microservers and also across different chassis. This is based on the one hand, PCI Express host-to-host, but can also be used as a high-speed, let's say as a raw high-speed serial interconnection among, for example, FPGAs. Okay, to give you more ideas about which microservers we are really supporting in here, these are not all microservers, but let's say the most common ones that we have integrated in the system. For the low power ones, these are, for example, NVIDIA Jetson TX2 or TX1. We also support the newer Jetson AGX or even or even NX fashion of these GPU SoCs. We have small FPGAs in there, as well as I said, the 64-bit ARM server SoCs, normal GPUs, and the quite big FPGAs in here, and can, as was shown in the video, integrate PCI Express or all kinds of PCI Express accelerators, which are there on the market. This whole thing, apart from just the cloud domain, is also available for the edge domain. It's a quite similar concept, really. So we are using the same microservers which were shown before. So, for example, the NVIDIA AGX or the latest Intel Xeon, also with, let's say, a quite similar communication infrastructure, but then having these integrated more towards the edge, which means that we have interfaces for much more interfaces for peripherals that can directly feed, for example, a video stream, or even specialized sensors for autonomous driving, for example, directly to those microservers here. All this in a quite compact dimension. This is shown here in the right, this small box here, and that basically allows you to do the same things that you are doing in the bigger systems. The Rex box systems can be also done here in the T-Rex, or you can also do here in the T-Rex systems, and you can even integrate these things here in, for example, our smart mirror use case that will be shown later on in the presentation, I guess, in Work Package 5, the use case work package. A quite new development in LEGaTO is that we are also focusing on new computer or module form factors, in particular COM-HPC. This is a picnic-driven initiative, which is quite industrial but large and open consortium trying to define the next generation of computer on module form factors. So complete LEGaTO hardware is compatible to this COM-HPC microserver form factor, and has also influenced the development of this new standard, as this is now in comparison to previous computer on module standards like COM-Express, not just focused on x86 technology, but which was then really driving towards heterogeneous architectures, and also including things like ARM or FPGAs in these formerly, let's say, x86 dominated markets. A quite unique feature for the LEGaTO microserver architecture, or let's say the overall Rex architecture, is a feature that is called node composition. The basic idea there is that you have your different compute nodes. Like here you can see a couple of ARM x86 GPUs or FPGAs at a quite abstract level, which are then let's say are being interconnected with different peripherals. For example, in this here it's an NVMe based SSD, and you can then, and say, even at runtime, most of the time this is done statically, combine these things together so that you really have a kind of software-defined computing. So here you can see that a couple of x86 nodes that is coupled to GPU nodes. I would say that's a quite traditional approach, but you can also have multiple FPGAs combined together via, let's say, dedicated communication infrastructure, and then even share peripherals. So for example, you can see that this NVMe drive here is shared by multiple of those composed nodes, as we say in LEGaTO, which means that every or all of those composed nodes have access to this single SSD here. This is basically done via shared functions. First, I would like to introduce the basics of node composition. As I said, the classical approach would be to have an x86, which is then, for example, just coupled to an extension card, for example, PCI Express. This is nothing special. This is just, let's say, as you plug in your GPU in your normal computer. But you can then, for example, also think of having multiple FPGAs composed together, and then having, for example, communication infrastructure with high-speed serial links defined across them. And you can then reconfigure this, for example, from a full mesh topology here to a ring topology, even, let's say, during the runtime of the application. What you can also do with this is you can assign virtual functions to multiple hosts. This is done basically, or this is provided by the PCI Express based communication infrastructure that we integrated there. Just to introduce everyone to this, the idea of virtual functions is that a single peripheral, for example, a PCIe network controller, exposes multiple virtual functions to different hosts. This is typically used in a virtual machine environment. I guess you all are aware of this and know this. The new thing here is that we are using this on the microserver level. So for us, basically, we are not using virtual machines, but we are applying the same technology to microservers. It then looks like this. We have that PCI Express switch, and we are talking about PCI Express host to host here. It means that we have multiple hosts or nodes here. For example, the x86 nodes, 2 of them, the NVMe-based SSD that we were showing before, as well as an FPGA microserver here. And we then have the communication infrastructure defined by this node composition mechanism, which, for example, looks like this. As said, this can even be changed dynamically during runtime. And what we can then do is we can assign virtual functions. The PCI Express switch has the feature of basically assigning these or a special kind of virtual DMA function, which can be compared to an let's say, or used like an Ethernet-based communication infrastructure, or for example, these peripheral, which is shown here in yellow, the NVMe-based SSD, which then has this virtual storage function, which is forwarded to the different nodes. So this is, let's say, how this node composition works on the different layers. On the one hand, only on the physical level, so that means the communication links by itself, and on the other hand, on the, let's say, virtual function level, where the different functions are being then mapped to the different peripherals. That all together provides a quite flexible system that can cover, let's say, a huge range of possible applications. These integrated communication infrastructure that I was talking about, so these virtual DMA functions can be used in 2 ways, either as a kind of virtual NIC, where you're using this like a socket-based Ethernet communication, or via RDMA, where you have basically use this via MPI or via verbs. And what you see here, or what you typically see, is for sure it's a lot faster than, let's say, a classical 10G Ethernet connection. As you can see here, this is a normal iPerf benchmark. We are getting up to or more than 50 gigabits per second, which is, I would say, quite okay for a PCI Gen 3 X8 link. And we are also very good on low latency compared to normal Ethernet. We are getting up to 6x improvement in latency, which is why we are also calling this the InfiniBand for the microserver. All this needs to be managed and let's say exposed to the upper layers of the LEGaTO stack. For this, we have on the one hand the kind of backend driver. This is done via Redfish, and this is then used on the upper layers of the LEGaTO stack. So basically the LEGaTO runtime, which will be presented in the next talk. And not just for node composition, but also for resource inventory, power control, and dynamic reconfiguration of the whole stack. And every Rexbox has also a web GUI. That means that you can have the same functionality that is used by the upper levels of the LEGaTO stack also available via let's say a normal web frontend, which you can then let's say, use individually to control the different nodes. Okay, so to summarize, we have this a quite flexible cloud to edge, as we call it, hardware approach that covers, let's say, everything from IoT to HPC. It's a heterogeneous microserver approach, which integrates CPUs, GPUs, as well as FPGAs. We are supporting latest COM-HPC microserver technology and these node composition mechanism, which I just explained in some detail. Office are quite flexible, and we think also really powerful mechanism for composing or assigning different compute resources to, let's say, different pools, and even sharing resources across those different pools of nodes. That's it from my side. Thank you all. Are there some questions or comments from the audience?
Sorry, I think Ayal had raised a hand, and I think he should be able to speak.
So at the moment, we are not able to hear you, or at least I am not.
I mean, he had this question like short after the video. Maybe he's not connected now, so maybe we can keep the question, or we can ask if he can ask later, or if he can comment it on the chat. He's commented in the chat. So what's the scalability of the system, and what's the largest configuration tested?
Okay, so depending on the actual configuration, or on the actual box that you choose, you can have, let's say, up to, for example, in the biggest system, up to 104 microservers in one rack, so in one box, so to say. So this is the low power one. So that means that you can, for example, have 144 of these NVIDIA Tegra GPUs in one of those boxes here. For sure, if you are going for high performance microservers, it will be less. It will, for example, be 27 in one box. You can then scale this up. So these communication infrastructure that I was talking about is scalable on rack level. The biggest configuration that we've tested so far, because this is still, let's say, in a kind of a prototype stage, was that we have an installation of, I guess, 3 to 4 of those chassis, but they were not populated with or just low power microservers. They were mainly populated with high performance microservers, which I guess was 9 high performance microservers with GPUs inside, which were then connected across the different systems. So we have not deployed this at, let's say, full data center level yet.
Thanks, Jens. I think I'll send a note that he got it. Okay.
Yeah, I see this. Yeah. If there are no additional questions, I would then pass on to Mustafa.
Thanks, Jens, for the presentation, and I'll share my screen now. I assume everyone is able to see my screen.
Yes, we see it.
Easy. Yeah, thank you. Hi everyone, my name is Mustafa Abdul Jabbar, and I will be talking about the LEGaTO software stack, especially the backend and the middleware of the LEGaTO project. The focus of this presentation will be the runtime systems that constitute the LEGaTO backend, which features energy efficiency throughout runtime techniques and hardware user schemes, and also fault tolerance, security, locality awareness, all of which are enabled through the OMPs and mostly through the runtime systems, which are the OMPs and the CTAO backends, and a few other innovations. Also, we will talk about the middleware enabled by the RxMaster, as was discussed by my colleague Jens, together with the Redfish API. So we just briefly highlight the integration effort in order to access the very heterogeneous LEGaTO hardware. So as you might have inferred, this is the outline of my talk. I will discuss the middleware in terms of the integration of the RxMaster with the Slurm scheduler. Then I will talk about the energy efficiency aspects of the LEGaTO backend, considering OMPs, FPGA integration, and the resource management granted by the CTAO backend. Also, the energy efficiency and the power consumption reduction achieved by FPGA, undervolting, and fault tolerance with GPU checkpointing. As you see, we have diversity of topics there contributed by several partners. So if I'm like, this is just a disclaimer. If I say something that's inaccurate, I'm interruptible all the way. So starting from the middleware, we would like to highlight the integration of the popular Slurm cluster management and job scheduling system with the RxMaster, developed as part of the LEGaTO toolchain. In this integration, the Slurm job scheduler is able to perceive the system partitions and limits from the Rexbox server. All of this is possible thanks to the integration with the RxMaster management software. So Slurm gets the node specification and selects the target nodes, of course, and it continues the normal function. As usual, it's able to allocate, join, and start the nodes of the Rex server, execute the application, and shut down the nodes and destroys the allocation. And here is an example of these are the resources as seen by the Slurm job management framework. So as I said, Slurm is able to contact the RxMaster, a job execution and termination. And here we see an example of such a way to do this communication, so that we have a constraint that is passed to the RxMaster. This constraints just specify that give me the ARM big little node that has a GPU, and such a constraint can be accommodated due to this integration. And also, as mentioned by my colleague, the composed nodes are also part of this integration. So the Slurm is able to see the composed nodes, which is another important feature of the RxMaster. And it's enabled through the API itself, the web API. And as you see here, so that's how the server looks, the entire cluster looks like. And here, when the cluster is enabled, we can see the color turns green, and it's all available to the scheduler. Next, I go one level up in the software stack to highlight one of the OMPs runtime energy efficiency features granted by the support of accelerators in FPGA devices in the OMS execution engine. Here we show an example of matrix multiplication that is offloaded to FPGA. The matmul block is defined as a task with input dependencies and signified by A and B and C, the bidirectional dependency from C, which is the output. Each call to the function will be converted to a task that will be run when the dependencies has been satisfied. The task has also been defined to be potentially executed by targeting the FPGA, and the accelerator is tuned by the programmer to exploit the parallelism of the FPGA by using some additional directives, such as the HLS directive, which are not really part of the OMS programming model. The figure over here shows the tool chain flow. The support is currently enabled on Xilinx FPGA using the Vivado HLS and Vivado tools through the Auto Vivado or Auto 8 tool. Now we show an evaluation of the performance and energy efficiency by the OMS FPGA integration compared to the CPU-only counterpart. On the bar chart over here, where the columns represent the G-flops performance and the line represents the G-flops per watt. In both cases, higher is better. We observed the best floating point performance using 3 IP cores, where the most energy efficient run is achieved by using 2 IP cores. And here we see the power consumption and the timeline that shows how the power consumption changes until the run has elapsed. And most of that power is attributed to the PL power that is due to the matmul known to be compute heavy kernel. Now the other runtime that is available in the LEGaTO backend is CTAU. In this part of the talk, I briefly highlight the runtime techniques developed as part of the CTAU backend, which are currently validated on homogeneous and heterogeneous CPU platforms, especially big LEGaTO architectures. I start with the an energy-aware scheduler that is composed of 3 main components, which are the power profiles of the different part of the system under representative workloads, a performance model that takes into account the performance of different system configurations, and the idleness tracer, which is an essential component that tracks the cores that has no work to do, but are actively pulling for work. The tracer is needed for considering also the static power of such cores when they are put to intermittent sleeps. All of these feed into task mapping algorithm, which predicts the energy of the task execution based on the above components, and it selects the appropriate configurations. Here we show energy consumption of running VGG16, which is a machine learning prediction framework on the TX2 heterogeneous hardware, which features 2 fast Denver cores and 4 A57 slower and more energy efficient cores. The composition, the comparison is done using different cluster level DVFS settings, max, min, and all the permutations are used here for different cluster level frequency configurations. The energy-aware scheduler is compared to representative baseline schedulers and is able to achieve from 20 to 75% over traditional work stealing and baseline energy efficient schedulers. CTAU also offers resource management of the underlying hardware using its expressive software topology address scheme, which is a portable key that is passed and interpreted by the runtime to map a task to a place. The place encapsulates hardware resources spanning a single core to many cores, similar to this figure that we see over here. The place also marks such allocation as shown by the figure. In this example, we use the space filling order to express a Cartesian input, such as the adaptive quad tree of the, for example, n-body problem. Since this order maps to a hardware place, it enables to create a performance model per locality using the software topology address and the task type tuple, hence provide an on-demand locality awareness for the scheduler. Here we just show a model validation in the interest of time. We just validate the model. We only show an experiment for a DAG chain, since it's hard to prove resource efficiency of the scheduler unless shown empirically. We print a trace of the subsequent schedules of tasks on top of DAG chain, where the data has been allocated on certain NUMA node. The tested system is a server hosting 4 sockets, each with 2 NUMA AMD nodes. The figure also shows the adaptive resource allocation. For example, in this case, it's a cache intensive task. It shows the locality preserving by choosing the places that share the L1 and mostly the L1 and L2 cache. And this is marked by the width of that such place. And in the case of memory intensive task, we see that for this system, the socket itself hosts 2 NUMA nodes. So the scheduler opts for running on 2 NUMA nodes spanning 12 cores within the initial location of the task. And also for the case of the compute bound tasks, it acts like a work stealing scheduler and considers the entire server to be potentially a place for execution. For the memory intensive experiment, we are able to achieve 2.5x improvement over the baseline locality aware schedulers. CTAO also supports multiple pipeline parallelism, which is a model parallelism, and that is natural scheme to utilize resources, especially when streaming inputs on heterogeneous devices, where the software stages has also complex characteristics that can be mapped to pipeline stages. The pipeline parallel capability is granted throughout a simple tensor language that is used to implement convolutional neural networks for labeling a stream of input frames. Due to the complexity of both the software represented by the layers and the hardware represented by heterogeneous platforms, an online training phase determines the optimal pipeline configurations, which are the network layer distribution among the pipeline stages and resource partitioning among the pipeline stages. I guess, and also, the train is also led by a search algorithm. The training is led by a search algorithm that utilizes computational hints that are given by the language interface, as you see over here. Since this is still a work in progress, we have preliminary results showing how the pipeline parallelism engine in CTAO reaches an optimal pipeline configuration, as shown by this simplified experiment over here, where the y-axis shows the span of selected pipeline settings. Starting from here, we have the 2 Denver cores and the 2 out of the 4 F37 cores. And this is running a 21 layered VGG network on 4 cores of the system to simplify the visuals. The figure on the right shows the correspondence between reaching a balanced stage of pipeline configuration to the reduction in latency of executing or predicting the label of a specific frame. Now we show a technique, and sorry for the bit of a diversion, but it's all within the energy efficiency scope of the project. So we show a technique that has been also explored in LEGaTO to target power efficiency in FPGAs, which is undervolting, FPGA undervolting. It is motivated by the fact that FPGAs are at least 10 times less power efficient than equivalent ASICs. So the goal of this work is to reduce the gap between ASICs and FPGAs in terms of power efficiency by developing techniques for and by exploring the effects of undervolting below nominal levels. And as a case study, we profile the power consumption of neural networks, which are of very important concern due to their diverse use in many applications. And we target FPGAs for this kind of experiment. So the experiment is evaluated using 5 image classification workloads on 3 Xilinx FPGAs, and the voltage, the internal voltage due to DSPs and LUTs is monitored. And interestingly, it was noticed that there is a large voltage guard band where you can run and not lose considerable performance, and again still get a 3 times power efficiency gain. So these are the 3 voltage bands that are explored. And we see that and it's pretty much large compared to the rest for the attainable guard band here, power guard band. So for this guard band, it's observed that there is no performance or reliability loss, and it is actually added by the vendor to ensure the worst case conditions. Yet when it was explored, the performance didn't degrade much for the application. And for the critical band, the accuracy of the computation has collapsed, and for the crash band, the FPGA stopped operating. And overall, the conclusion of that is that there is a slight variation of voltage behavior across platforms and also benchmarks across the x-axis. So there was no much variation in the voltage behavior. Last but not least, we highlight the fault tolerance aspects of the backend enabled by the GPU checkpointing with the FTI, which stands for fault tolerance interface. This work enables checkpointing the data both on the data that exists on either on CPU and GPU throughout utilizing the pinned memory to reduce the GPU to CPU data transfer overhead. The MD5 algorithm is completely executed on the GPU device. Then the host to device engine, which in a sense sends the data to GPU for checkpointing, that's followed by a CPU task and an IO task in a pipeline manner in order to output the checkpointing data to persistent storage. It's worthwhile mentioning that the parallel streams are adopted in the IO in order to improve the efficiency as well. So the figure here shows the speed up experiment comparing the checkpointing on GPUs versus CPUs to show the performance of the GPU MD5 algorithm. It's observed that we have up to 100 times speed up that is achieved as you increase the memory allocation, yet you expect more overhead due to checkpointing. As far as the overhead itself is concerned, the checkpointing takes less than 1 second, whether using 1 processor per GPU or 8 processors per GPU with different counts of GPUs. Yet the performance of the GPU MD5 algorithm does not seem to significantly degrade by an 8-fold increase in the hardware usage. I guess with that, I would conclude my talk. Thank you for listening. And if you have questions, please feel free to ask.
There's no questions. Thank you, Mustafa. Next, we have Pascal Felber. Pascal, you can take over. Thank you.
Okay, do you hear me?
Yes.
So let me share my screen. Can you see the slides?
Yeah.
Okay, good. So we're going actually up the stack of LEGaTO, and this presentation is about the programming models of LEGaTO. So I will go briefly over a few of the major outcome of this part of the LEGaTO platform. So we'll discuss a little bit about programming models in the big picture of LEGaTO. We'll talk about the programming models for different targets, targeting FPGAs, GPUs, and so on. We'll focus on energy efficiency. We'll show also how to get the data flow task go on HDL, and the kernel identification and data flow engine mapping. And finally, we'll conclude with discussions on fault tolerance and security in the big picture of LEGaTO. So this is the stack picture that you already saw. The green boxes are actually the items that I'm going to talk about now. And they are identified in this higher layer of programming models and compiler and HDLs. So the main achievements we had in this part of the stack are first the programming models and annotation that support the programmer into building highly efficient heterogeneous applications. Then we'll discuss about, I'll show what we did in terms of compiler support at different levels, mainly focusing on ARMS with backend to GPUs and FPGAs. We'll talk about the task model that is provided by ARMS, and I'll briefly explain how it goes through LLVM code generation to also output to a target on Elastic Clouds. We have developed a plugin for Eclipse, the Eclipse IDE. We have support for grouping tasks and partitioning resources, and then doing some scheduling for optimizing energy efficiency. The task scheduling is done at the level of Shitao for mapping the task in Elastic Clouds, and also at the level of at a higher granularity for by heats, which does mapping of containers, and Dias, which supports printing. We have developed a high productivity HDL called Defiant in this project. We have a way to output the OMS task directly onto MaxJ, And the fault tolerance is provided by compiler-based error detection. We have co-scheduling mechanisms, checkpointing also for fault tolerance, and there is security built in by the option to execute tasks within trusted execution environment on hardware. So the overall concept, the overall goal of LEGaTO is to have a single source for multiple targets. So we are actually witnessing a world where you have new architecture, new hardware architecture that continue to appear, but we don't want to change the programming model for every single new architecture. So we target a common programming model that will be comfortable for the programmer in a way that it can improve the productivity. We develop the code once, and then we can target the code to multiple targets. With the goals of having both performance and energy efficiency. So this is actually part of the goal of OMS. The key concept of OMS is you start from sequential tasks that are based on a single address space, plus some annotation. And these annotations will then enable to build software that tasks can be executed in parallel on multiple hardware. And the choice of the hardware is driven by considerations like memory, energy efficiency. And it can change actually at runtime. So on this picture, you see the front end. That is what we are concerned about in this presentation. So you start from source code in OMS, and then you go through static kernel identification and code generation. Then this code can then be mapped to different execution substrates, which are FPGA, GPU, or Shita. And so we have two high-level programming methodologies to generate code in here. HDL, it's Defiant, and MaxJ. So just to have a quick look at how things look from a programmer perspective, you can have an example here of pragmas that you can insert in your code. So this is, for instance, a matrix multiply, classical matrix multiply algorithm operation, and you can have different implementations. You have the usual scheduling policies for the task, like FIFO, SILK, and so on. And then using the keyword implements, you can provide different targets for the same task. The kernel will be can be provided, for instance, in CUDA or in OpenCL, and the data transfers are automatically issued by OMS, so you don't have to care about it. So you start from a single source with different targets and different implementations that target different kernels, and then from there on at runtime, the code can be run on one or another. So this is a quick view of some of the results we obtained, some of the experiments we run when running OMS with FPGA on different configurations. So different configurations. So this is running a matrix multiplication of 248 by 248, and it shows the performance in gigaflops. Depending on how many cores you use, how many FPGA helper threads, and number of pending tasks that you consider, and also the frequency of the FPGA board, you can really gain, in this example, up to 1 order of magnitude better performance by running the right configuration. Then, in terms of productivity, in terms of ease of development, we have developed a plugin for the common, the popular Eclipse IDE. So it supports OpenMP and OMS directly within Eclipse. It provides support for most of the programming model directives and flows. It has also some help files, and it supports context, auto-completion, and the usual stuff. So this has been developed as part of LEGaTO, and it's provided together with LEGaTO. There's the work that has been done on providing a hardware description language, high-level HDL Defiant. The goal is to bridge the two extremes. On one side, the software, on the other side, hardware, and bridge that with data flow languages. So it's a middle ground between what you do at the low level of the HDL and the high level you usually do when you program with high level sequential languages. So on one side, you got the architecture with HDLs. On the other side, you got the high level programming model with algorithms. And at the level of HDL, you have fine support for concurrency and fine grain. On the other side, you have support for things like automatic pipelining, and Defiant is providing this middle ground that will actually combine the best features of both. And the way it does that is by separating the timing from the functionality. This is one of the key concepts of Defiant. In terms of task mapping and task identification, so we start from OMS starts from the task graph that is built at runtime, and it will identify static task graphs out of these graphs. It's also exploiting annotations to identify these graphs, and using that, it creates the DFE task model that it can then instantiate within the hardware. And it can also provide support for identifying static subgraphs and combine them into macro tasks. For instance, here in green, we see one macro task that has been identified with inputs and outputs, and this can be mapped as one bigger task directly on a FPGA or on HiTao. HiTao provides support for a parallel deployment of tasks on parallel nodes. It's designed again for energy efficiency. So the nodes will hide the complexity of things like internal task parallelism, and they can be scheduled as a whole with the scheduler of HiTao. It provides programmability. It has an interface in C++. You have only very few code changes to apply to application to run it on HiTao. It supports task and data parallelism with an intuitive nesting of data into coarser-grained DAG graph. And it also provides different levels of granularity for the thread to core mapping. So you can also play at that level and control how many threads are mapped on a given core. Then we have another level of scheduling, which is at a high level, at a more macro level, with heats. It's a scheduler that has been built also to take into account heterogeneity and energy awareness in the scheduling decision. And it can schedule the complete containers. It runs with a Kubernetes. So Kubernetes containers can be migrated and scheduled depending on constraints based on energy. And it also supports monitoring. So it will monitor at runtime the consumptions and the needs. And based on the input from monitoring, the scheduler will kick in and migrate whole containers. Then there's another also way of optimizing energy efficiency at the level of the scheduler. And this has been explored in another tool that we built called DIAS. The observation is that you have jobs with very different characteristics and latency requirements, and also the number of tasks is varying a lot at runtime, and the priorities also have to be taken into account. Rather than using preemptive priority scheduling, which will be a waste of resources and a waste of time, we actually try to see if we can use sprint CPU frequencies to optimize the execution time of specific tasks and finish them with a higher priority. So the last point I'm going to talk about in this presentation is fault tolerance and security. So there are, on the side of fault tolerance, there is support for doing checkpoints. So this is provided at the level of software, you have to add some annotations and in your program, and they will be translated into calls to the fault-tolerant API. Then at runtime, these mechanisms will support incremental checkpointing on the fault-tolerant interface, and you can use that to also implement partial recovery if there is a failure that occurs at runtime. This is completely transparent to the programmer. Then the last point is about security. Most of the work was done in the context of the Scone platform. Scone is a platform that allows to compile and run unmodified software within the Intel SGX trusted execution environment, so within enclaves. You don't need to change your code, you just need to run with a specific compiler toolchain. And it provides support for attestation of application. It supports, it shields your application at the level of the file system and the network. It will provide secret management and secret configuration. And it has been tested and validated using machine learning computations on different systems. And it's also relatively energy efficient in the sense that it doesn't require additional computations besides running in a hardware enclave. So to summarize what we discussed at the level of this software stack, there's the aspect of heterogeneity that is built in around OMS. So OMS is a single language that can then target heterogeneous hardware. Energy efficiency is supported by mainly the scheduling mechanisms in Cheetah, but also in the other tools. The programming model are based on pragmas in OMS and then the code generation, and also support via the IDE. There's a common programming model for the different targets. We have the high-level data flow hardware description language that is supported also in LEGaTO, that was developed in the context of LEGaTO, and then the data flow engine with identification of the kernels and the mapping, and finally the features of fault tolerance and security that were added to the system. So that's pretty much what we achieved in the context of this project, and everything is actually quite integrated, tightly integrated together. So that's the end of my presentation. If you have any question, please ask, and maybe you can also ask some of the partners who know one or the other aspects a bit better than me. Does anyone have any question? Common model allows migrating between targets.
If I may?
Sorry, yeah?
This is Xavi.
Yeah.
So I understand Ayal asks for the possibility to, let's say, execute the same task on different targets.
Yes, can you hear me now? I'm having
yes, we can hear you.
With the other. Yes.
Hello.
Sorry for my difficulties. But yes, the question is if the model is common in the sense that the same snippet of code can run on one target and then can seamlessly migrate to run on another target.
So we have the issue of the different target compilers, which we cannot control. We cannot control the NVIDIA compiler, we cannot control OpenCL, and we cannot control the generation of the bit stream. So at that point, we need to provide actually different codes, but they are started from the same task, from the same invocation point, I would say. In fact, I'm showing that in my presentation in a few minutes.
Okay, good.
Good.
Thank you, Pascal. Maybe we can continue with the use cases with Micha. Micha?
Okay, I hope you see my screen now.
Yes.
Yep.
Perfect. Yeah, then let's start right away. I will give you an overview about the use cases of the LEGaTO project, presenting, first of all, what the use cases do in general, and then also highlight and explain how we optimize them using the before presented LEGaTO workflows. So in general, in work package 5 of the LEGaTO project, we developed and optimized different use cases and also built demonstrators to show what we did here. We integrated or developed components. So from bottom to top, we have the hardware, firmware, middleware, and runtime, front end and back end. So all the presentations that we heard before. And we evaluate the project objectives. In this overview that you see here, we are at the very top of the overall view of the LEGaTO project.
Sorry, Micha, there's some flickering a little bit. I don't know if it's on my screen.
Seems like your background is somehow flickering through the presentation.
Ah, that's not good. How could I fix that? We tried that before and it worked smoothly, right? Otherwise, let me try to stop my sharing here and try to share a complete desktop. Maybe that makes it better. Do you still have this flickering now?
Yes.
Yeah.
It is still there.
Oh, that's a pity. Then let me try something else. I could try to present it directly here on Linux. Hopefully the layout of the presentation is then not completely broken. Please give me a minute. Okay. Oops. How about now?
Still somehow, yeah, there.
Oh, okay. Then this is obviously a general Linux problem.
But we can still see the contents. It's just very instantaneous, I'd say. Very short period.
Otherwise, let me try to log in separately using my remote desktop here. Maybe this
or maybe
also...
not to use the full screen.
Yeah, maybe you can take it out of presentation mode and just like, you know, show the different PowerPoint slides one by one.
Yeah, if that works. Is it better now?
No, it still happens. Oh, sorry. Didn't work out.
Sorry, if anyone has the PowerPoint, maybe someone else can share the screen.
Yeah, I was thinking with that.
I'm downloading it. It's version 3 from the intranet.
No, it's version 4 actually.
Okay.
But let me try to share my screen here now. So do you see my screen now?
Yeah, it's good.
Okay.
Okay, then let's proceed like that. Sorry for this inconvenience. Yeah, when trying this out a bit earlier, it worked fine. But nevertheless, let's move on then. Okay, as you can see, we have 5 different use cases. The first is smart city, then we have smart home use case, infection research, machine learning, and finally a secure IoT gateway. And we will now go through them one by one, and I will shortly explain, first of all, what the use case is about. The use case of the smart city is about air quality forecasting in urban areas. This runs a CFD simulation with a program called ALIA. It is developed in Barcelona Supercomputing Center and also running there at this moment, and is based on real sensor data from Barcelona city, which are spread across all the city of Barcelona. So we will concentrate just on the core program of ALIA here now today. The initial optimization plan of this use case was to allow more complex simulation by reducing the execution time and make use of FPGAs, and finally also port this to OMSET FPGA. We found 2 main compute kernels, which is an explicit momentum solver, which uses roughly 60% of the total computation time, and the sparse matrix vector multiplication, which uses roughly 10% of the total computation time. While analyzing and going on in this optimization process, we found out that there are some incompatibilities between 2 of our tools and Fortran, and we had quite a lot of, or we experienced quite a low performance in the FPGA implementation, running the sparse algorithm. So we finally changed towards a different architecture, namely the NVIDIA's Xavier GPUs, and ported the linear solver to exploit this architecture. And we compared then the program running on the NVIDIA Xavier modules to the Mare Nostrum 4 supercomputing node, just one node, so one node x86 versus one node of this ARM Xavier modules. And you can see on the left that we have a quite impressive improvement in terms of energy efficiency, depending on the node and the number of modules of Xavier modules that you run in parallel. So on the very left side here, you see the Mare Nostrum energy efficiency. Here we have 2 different energy modes running one Xavier module, and here we have again the same energy modes, number 0 and 3, running 2 Xavier modules at the same time. Because of the overhead running on 2 modules, you see that the energy efficiency drops when you run 2 modules in parallel. And on the right side, you can see that in total, the execution time running on the Mare Nostrum CPU is 6 times faster or 6 times lower than running on the Xavier module in energy mode number 3. Yeah, so finally it's up to a user, or finally up to you, what is more important, energy efficiency or execution time, as initially also set by in the first presentation. Then the second use case is about smart home. We did a smart mirror prototype here as an intuitive interaction interface for a complete smart home or a flat installation, which can display personalized information on a mirror surface and also can be controlled by gestures or voice commands. In the background, there are quite a lot of neural networks running and analyzing what cameras can see. For example, we have YOLO for object and gesture recognition. We have wider face and FaceNet for face recognition, and Mozilla's deep speech for a speech recognition. And finally, we are then have many more features in development, which are all packed in this smart mirror demonstrator, and they all interact together to make a quite unique and interesting look and feel. The idea is, and always was, to develop this based on an implementation of a installation that is already existing in a research department in the city center of Bielefeld. In the middle here, we do not have to focus too much on all these different things. What is important here is that we just focused on some of these modules that we implemented to be run on this hardware on the left side, the NVIDIA Xavier module. And theoretically later on, we could also think about in further projects to use further FPGA modules or other hardware modules to optimize further of these modules. To give an overview of what we have in terms of energy efficiency or hardware setups also. The evaluation metrics were in general the performance. So we need a total performance of 5 to 10 frames per second to ensure a smoothly running demonstrator. Otherwise it will just stutter, and this looks really weird. And also we had a total power consumption goal of maximum 50 watt to not blow out all energy just for a simple mirror application. So combining these two things, we have then a goal of a specific energy efficiency. The first prototype that we developed at the very beginning of the project, we used these GeForce, two GeForce 1080 Ti graphic cards on a up-to-date Intel i7, and we were able to achieve 12 frames per second running at 650 watts. This is quite massive power consumption, and we really wanted to go down. So what we have achieved then in the second prototype is we improved the frames per second, so improved the performance, and also went down with the power consumption a little bit, but the massive but the massive improvement in energy efficiency were then achieved when going to embedded hardware prototypes. This can all be seen here in these nice graphs. So starting here at the top, the starting point in frames per second, we had a bit more than 10 frames per second, did some optimizations to speed up things, and then moved to embedded hardware, which dropped the frames per second quite a lot. But if we use two of them, we are at 15 frames per second, which is more than perfect. In terms of energy consumption, we dropped also quite a lot using these embedded hardware modules. And if we have a look at the last slide here, which is the energy efficiency, so frames per second per watt, we are right now at exactly what we wanted to achieve. Coming to the third use case, which is about infection research. This is a quite statistical use case, running quite a lot of mathematical things in background, but the goal is to use these statistical methods to research the effectiveness of drugs and vaccination strategies, and also harmfulness of pathogens. Today, in this COVID-19 situation, this is really a quite important thing, really, that we need here. The basis is always that we have some pilot studies with very small sample size, but a large number of features, which are biomarker candidates usually. And then we want to distinguish real correlations from random correlations. So we want to find out whether there's real data in the metadata sets. And our strategy is to select the top features from thousands that can predict the case, and then estimate the appropriate sample size that we need to get significant results. The optimization goal was to decrease the simulation runtime and enable larger data sets and more complex problems, because the initial runtime, simulation runtime of some of the problems that we wanted to run are so massive, like in the area of several months or even years, that it's completely unrealistic to simulate some of the problems that we wanted to use. And the side effect, honestly, was we wanted to decrease the energy consumption by decreasing the runtime. This whole tool flow is here written down in 4 different steps. And these 4 steps that I already, in a bit different manner, I explained before, were accelerated using different tools from our LEGaTO toolset. In the first one, we used the Maxlar data flow engine and achieved a massive speed up of factor 822, which is really true, not fake news. Then in this third step, the second is quite easy and simple, does not need to be enhanced, but the third step was also again optimized using different tools and also LEGaTO hardware. We had here speed up of factor 40, and then using ohms at FPGA, factor 10 of speed up. And we integrated SCOAN to enable data security. And finally, in the last step, we accelerated using the XiTao framework and are achieving right now a speed up of factor 3, but are still in the optimization phase. And then the fourth use case is about machine learning. The motivation is that machine learning is very powerful, as many people might know today, but still has a high power consumption and high computational time due to large amount of signal precision, or in general computations needed here. Our goals are to decrease the energy consumption by factor 10 and also the inference speed up by a factor of 10, while increasing the throughput and reducing the latency of running these modules in the inference. Interestingly, we are doing this on different hardware types, as you will see in the next slide here. Just a second. Okay, needed a bit of water. The deep learning optimizer tool that we developed within this LEGaTO tool uses, at the first step here on the left side, user models and some requirements, for example, from TensorFlow or MXNet or different other tools here are planned to be supported later on, and translate this then into an intermediate representation here, which is then used and optimized using these application requirements here on the downside. And then this deep learning optimization engine here is used to finally put out specific models that target our specific hardware candidates. So here we have named a few of them, for example, the NVIDIA TX2 or NVIDIA Xavier modules that were named before in the use case, or FPGA Xilinx ultrascale modules here on the right side. And then we use our ohms driver to run this later on our evaluation server. We did quite a lot of benchmarks here. To make it quick, we achieve in some of the use cases and some of the hardware, we achieve this factor 10 in terms of energy efficiency and also in terms of speed up, but not in all of them, really highly depending on the model that we are looking at. And then finally, we have the secure IoT gateway, which we developed in the project. This might be a typical IoT scenario. So we have 2 different customers, each is having some devices and a network gateway and is sending unencrypted data to a data center. We wanted to encrypt all these things. So we put in a gateway cluster here at the top and the network in the data center, and are ensuring an encryption data through a VPN secured connection to also then network gateways here, which we provide and specialized IoT bridges, so that everything from the IoT bridge until the data center and potentially also other customers can be completely encrypted. But as this is quite complex to set up, we also developed a network cockpit to do all the management stuff for you. This looks like this. This is just one of the screenshots of our network cockpit that you see here. And it features quite a lot of quite interesting things, having some device statistics and really doing these complete management mechanisms for you, whether you, for example, want to allow different IoT devices to communicate between each other or not, and many other things. This is then used in the LEGaTO project to support the smart home use case. Originally, it was also planned to support the smart city use case in Barcelona, but there were some hurdles we could not overcome. Our evaluation metrics here are the usability, network performance in general, so comparing without encryption and with encryption later on, and the total costs of ownership, comparing our solution to a traditional securing use case. Okay, that's it. Thank you very much. Any questions concerning our use cases and optimizations? Okay, if not, then I guess, Xavier, it's your turn.
Thank you. Let me share the screen. And do the slideshow. Can you see the slides?
Yes, we can hear you and see the slides.
Okay, thank you. So this is Xavier Martorell. I'm going to present a little bit the summary of the LEGaTO integrations at the level of the programming models. So I will show the integration of OMS with the various runtimes that we have: HiPEAC, CUDA-OpenCL, Xilinx FPGAs, Defiant, Maxeler, and SGX, and then briefly the linter tool and the Eclipse plugins. And I will conclude and present future work. So in all the slides where I introduce one of the integrations of OMS with the associated runtime or programming model, I show a kind of figure like this, in which we indicate so how the application is written, who is responsible for splitting the code, and how the final target is generated. So in this case, the integration is between the tasking model of OMS and the tasking model of HiPEAC. We determined that given that the two styles of programming are actually different, the programmer splits the code of the application and writes the portions of the code that are amenable with nanos using OMS, and the portions of the code that are amenable with HiPEAC with the C++ extensions that HiPEAC uses. And then we did the work in order to have the two runtimes, in that case nanos and the HiPEAC runtime, to interoperate in the sense that they split the cores that we provide to the application. We use, in fact, the common tool task set in order to distribute the cores between the two different runtimes. And then everything gets compiled with GCC, we link with the runtimes, and we get the binary. So as an example of code, we use matrix multiplication as a common benchmark in order to display how to write the code in the different integrations. So here I'm showing the integration of the tasks written in HiPEAC. So that is the code that the programmer would write using HiPEAC. This is here the code that the programmer will write when using OMS. And then the execution mixes the two styles of tasks. And for instance, in this case, we did a small benchmark which splits the matrix multiplication using tasks from Shitao and tasks from OMS. And at the end, we verified that the result is okay. So this is one of the integrations. The second integration that I'm showing here is the integration of OMS with OpenCL and CUDA kernels. So in that case, the application is written at the high level in C or C++. The programmer needs to provide the CUDA files or the OpenCL files here, or both, in fact, because we achieve it to run applications mixing CUDA and OpenCL on different targets, okay? Mercurium has these two phases, the OpenCL phase and the CUDA phase, which deals with the different files. The CUDA files, in fact, are provided directly to the NVIDIA compiler, and the object file that is generated from the NVIDIA compiler is linked with the object files that are the host part of the application. The OpenCL files, in fact, are managed differently depending on the target. If the target allows like runtime compilation of the CL files, they are provided to the CL compiler at runtime. Otherwise, in fact, for FPGAs, for instance, we compiled on the first hand the OpenCL files, and then we provide to the runtime the binary version of those files, which in fact is the bitstream that we use to program the FPGA. And I think here is the key is what we call the implements clause in OMS. So here I'm showing a possible writing of the matrix multiplication kernel for SMP, in which I'm calling the CBLAS optimized version of that would be a block by block matrix multiplication. So we annotate that kernel with the directives that have been already presented in previous presentations. They have appeared, in fact, in BP3 and BP4. Targeting the device SMP with the proper ins and outs for the matrices, okay? And we also provide the kernel written in OpenCL, and we say that this kernel implements the previous one, matrix mult, and we also provide the kernel written in CUDA, which also implements matrix mult. So given that we have these three different implementations of the kernel, the application is exactly the same up to this point, up to the point where matmul calls the kernel implementation. And here, the runtime system is informed that we have SMP, GPU, and FPGA version, so it is able to invoke the kernel in several or all of them, okay? And this is what, in fact, this plot shows. It shows that I can run OpenCL FPGA, which is the native version of an OpenCL implementation on an FPGA. This is currently running on an Intel Arria 10, okay? I can run on the SMPs. I can run with OMS on the FPGA using OpenCL. I can run on the FPGA using additionally several SMP cores. I can run OpenCL on the GPU. I can run OpenCL on the CPU. Here, the performance of OpenCL in the CPU is very low because in that particular implementation, I'm using MKL. Here, OpenCL is not offering the same performance because I'm using the source code. Okay. I can run CUDA on the GPU. I can run even QBLAS on the GPU. I can run OMS with different number of cores on the GPU. And at the end, I can run OMS with CUDA and the FPGA. Okay, and here the question would be why this performance is so low. And my answer here is that given that we have different performance on the cores and on the CUDA GPU and on the OpenCL FPGA, it's very difficult to tune the performance that you obtain from the execution of the application when using heterogeneous resources. Okay. So in fact, you can see here, in fact, that the best performance is achieved with the GPU, okay? But it's actually very competitive also using only the cores of the machine, okay? Because this is using MKL. Also notice that, in fact, the performance on the cores is reaching probably very close to the peak with 4 cores, because the rest are just hyperthreads. You can see here that there are 2 hyperthreads per core. Okay. So this is a little bit the exploration that we can do with benchmark that we have written in this with this approach. Okay. So another integration that we have done is the integration of OMS with HLS kernel, which is very similar. In fact, it's only replacing CUDA or OpenCL with the HLS implementation of the same kernel, for, in that case, for matrix multiplication. In the context of LEGaTO, we have been porting our infrastructure to the ComExpress board, also to the Alpha Data FPGAs, and recently we got also the environment running on the Alveo U200. Okay, so just for comparison, here the target device FPGA targets the FPGA, and the target device SMP targets the cores. Okay, so and then in that case we don't have CUDA, but we will be able to do the same type of analysis on the execution. Okay. Another integration that we have done is at the level of HLS, where we replace the kernels that we provide to HLS by the defiant kernel. So this is the high-level description language that has been designed in Technion, and we use that description language to generate the matrix multiplication kernel. It gets compiled with a defiant compiler and integrated on the integration of all the IPs that we have inside our auto IAT tool, and then it becomes part of the bit stream. Okay. So another integration with which we are experimenting is the integration of Maxeller kernels. So here, the programming in fact splits the code, because we need to rewrite the kernels in MaxJ in order to be compiled with the MaxJ compiler. But then the integration is very similar also. We have extended OMS in order to support the invocation of the MaxJ kernels, okay? And then all this runs on the Maxeller FPGAs. So in that sense, it's very similar also to CUDA and OpenCL. And then we have had also experimenting with the execution of secure tasks. In that case, the programmer adapts the tasks to use the SGX from Intel. We compile the tasks to become part of an enclave, and then OMS is able to run the application and run those tasks on the enclave. And we have done also several experiments with a few benchmarks, matrix multiplication, and body, and we are trying to see if we can do some experiments also with the machine learning darknet environment. Okay. Additionally, OMS has been extended with a linter tool, which is a tool that uses debugging information and tracks all the inputs and outputs from the tasks and determines if we have any data races or any missing clauses in the directives. So at the end, you get a report saying what are the missing things or what the tool thinks is a mistake in the annotations. Okay. And then we have the IDE plugin, which allows you to write the applications with Eclipse. And Eclipse suggests which are the directives and clauses that you can use at any point. And then we have an integrated environment where you can tell the environment to compile the application and generate the bitstream. Okay. And that's the, let's say, collection of integrations that we have been developing. I would say we have a good support for GPUs, HLS, and OpenCL FPGAs. I think it's very interesting, this implements approach in which you can run the same functionality on the different devices. And we need a lot of tuning there, probably better scheduling at the runtime system level may improve the execution when we use the 3 devices, let's say. We have done experiments with the task scheduling with OMS and Chitao. We have the prototype supporting Defiant, Maxeller, and the secure tasks, the linter, and Eclipse. So we are now preparing a joint code distribution with all these contributions. And we will do further experimentation with the LEGaTO benchmarks. And that's the presentation. So if you have any questions, let me see the chat. In fact, I think I cannot see the chat. If there is any question, let me know.
So there's no questions as far as I can see.
Okay. So maybe Osman,
okay.
You have the word.
Thank you, Xavier. I think this concludes the workshop that we had on different features that we developed during the lifetime of the LEGaTO project. We still have a couple of months life in our project. And we hope that the tools that we developed during the project will have an afterlife after the project ends. If you are interested, please contact us, and we will for sure would like to discuss like this afterlife options. So, is there any general questions or comments?
I just want to add, Xavi, Osman, and everybody, this is really cool stuff. Thanks for sharing.
Thank you.
Thank you. Thank you.
So
okay.
Maybe one more comment. So we will share on the chat the link to a small questionnaire that we prepared and that we would like the people that has been attending the session to fill in, so that we can get some feedback from this session. So let me post the link. Yeah. So we let a bit of time before closing so that people can type on, check this this link. It's just a couple of minutes or less.
Salazar, thank you. I think the link has been there for a little time, quite some time for folks to click on it. So with this, we would like to conclude. Thank you very much, everyone, for attending, and hope to see you in other endeavors and other workshops. Thank you very much. Bye-bye.
Thank you.
Thank you all.
Thank you.
Bye.
Bye-bye. Thank you.
Bye. Thank you.